Okay, so for this last one, I want you to go into Top Hat and answer this question so you get credit for doing the lecture. Okay, and all of these elements are a combination of a metal and a non-metal. So that means that they are ionic compounds, probably. On the other hand, if I have two things which are non-metals, it's likely to form a covalent bond. So here, for example, we have hydrogen. We can draw the Lewis structure of hydrogen. It's just one dot for each of them. In order to make a stable bond between these two, if one hydrogen gave up its electron to the other one, then it would have a plus charge, and the other one would have a minus charge. And nonmetals don't like that, especially because they're both the same element. So how do you pick which one gets the plus and which one gets the minus? So instead, we don't do that. We actually just share the electrons, right? They get to share them. And what that means is that if we draw a picture of the electrons and where they like to spend their time, mostly it's in between the two atoms. So we draw our Lewis structure here to reflect that. Okay, so here's another one. Here's the carbon dioxide. Okay, so I'm going to draw carbon as red. And I put it in the middle because it's the first atom that's listed in the compound. And usually the first atom is the central atom, unless that first atom is hydrogen, in which case it can't be in the middle because hydrogen can only have 2 electrons, like we saw up here. So, but carbon doesn't have that problem. Carbon can be in the middle, and carbon starts out with 4 valence electrons because it's in group 4. And it's paired here with oxygens. I like to write the oxygens on either side because generally nature likes to be symmetrical. Okay, and so I'm going to draw my Lewis structure like that, and they're the same. They're both the same element, so the oxygens are going to look the same. And when I draw it carefully, when I draw it this way, one dot on each side and then filling up as I need to, I can see that there's 2 electrons here that really want to form bonds like that. So one of the carbon electrons bonds up with one of the oxygen electrons, so that creates what we call a single bond. 2 electrons together is a single bond. Then we do the same thing again with electrons between carbon and oxygen, so that creates another bond. So now in between this carbon and this oxygen we have 2 single bonds, which together culminates into a double bond. That means there's actually 4 electrons involved there. Over here we have a similar thing, so those 2 electrons form a bond and these 2 electrons form a bond. So if I want to draw this neatly, then what I do is I write oxygen with it still has these 2 unpaired electron sets out there, and then carbon in the middle, and then oxygen with the other 2 electrons there. So this is the Lewis structure of CO2. I wouldn't leave it like this on a test, like this ugly one here, because it doesn't look very symmetric and it's not very pretty. And so usually I do a rough sketch and then I make a prettier one and circle that one for my final answer. Now, so this is our Lewis structure here. You could also draw it as dots. Okay, so this is still a double bond because it has 4 electrons involved. 2 of them are from the carbon and 2 of them are from the oxygen. But they're shared, so we draw them as in between the 2 atoms rather than transferring them completely like we were doing with the ionic compounds. It turns out that in this particular example, 1 s electron and from each of them pair up to create one of the single bonds, and then from each of the atoms we get also 1 p electron, and that also pairs up. And so the p electrons become what we call pi bonds right there. That's supposed to be an arrow, but it doesn't look like an arrow. So the pi bonds are actually above and below the plane of the molecule, and the sigma bonds are in the plane of the molecule. So here the sigma bonds create a line all the way through the molecule, whereas the pi bonds kind of exist in this cloud above and below. So there's 1 pi bond right there, and there's a second pi bond here on the other side of the molecule. And it turns out those pi bonds are important because they're on the outside of the molecule. So anything that's coming to attack this molecule is going to end up running into that first. So pi bonds are vulnerable. I can't fit that in here, but you can write that down in your notes. They tend to be the first thing that reacts in a particular complex. So identifying these pi bonds is a really important step in deciding how the molecule is going to interact with the rest of the world. Okay, now I said there's a different method for indicating when you have an ionic bond and when you have a covalent bond. In order to figure that out, we need to use what we call electronegativity values. So electronegativity values are just a big table. This is provided to you for tests, so don't try memorizing this. You do want to be consistent about which table you use. It's probably better to use the one in the notes rather than going to the internet. But for any given compound, we can use the difference in electronegativity to help us figure out if it falls into one of these three categories. The first one is something that is nonpolar, meaning it's an entirely covalent bond, and the electrons are shared equally between all the atoms. So we just saw an example of that when we drew the hydrogen molecule. And this has to be shared equally because hydrogen and hydrogen are the same atom. You can't choose to spend more time with one or the other if you're an electron. On the other hand, if we have something more like, oh, let me see here, chlorine connected to a hydrogen, that is what we call a polar covalent bond. It means there's a partially positive charge on the hydrogen because hydrogen doesn't like electrons very much, and a partially negative charge on chlorine. That partial sign is a little lowercase delta, which you can draw. It kind of looks like a D shape, like that. On the other hand, if we had a really huge separation in charge, like the electrons never spend much time between the two atoms, right here, then we would call that an ionic bond. So we can use the difference in electronegativity to help figure this out. If it's bigger than 2, it's an ionic compound. If it's less than 2, it's some kind of covalent compound. Okay. Normally we would say that only electronegativity differences of 0 are nonpolar. So anything bigger than 0 but less than 2 is covalent, polar covalent. And anything at 0 is nonpolar covalent. Anything bigger than 2 is ionic. Okay, so we're going to use this table here to help us figure this out. So we have that carbon and oxygen structure we were looking at before, CO2. And the question says, what's the difference in electronegativity between these two things? So when we look at electronegativity differences, I'm looking at the difference between just two atoms. I can't compare an entire complex. I have to look at just a single, like one bonding area. So between this carbon and oxygen, I go back here and I say, okay, carbon is 2.4 right here, and oxygen is 3.4. So 2.4 and 3.4. So we're going to take the big one and subtract the little one. And the difference between them is 1. Okay, and then I go back to our chart here, and we said, okay, a difference of 1 falls somewhere in there, the polar covalent area. So it's polar covalent. And if we wanted to be completely accurate, we would also say it's a polar covalent double bond. Because covalent bonds can be single, double, or triple bonds. So we should probably specify. For H2, so we had a structure of that looks like this. And our value of H, it's over here. It's kind of in a weird spot, but it's 2.1. So we go 2.1 minus 2.1, so our value difference is 0. There is no difference between them, which makes this a nonpolar covalent bond. So we would write nonpolar covalent. Okay. Nonpolar covalent bonds can also be double, single, or triple. So in this case, we would say a single nonpolar covalent bond. And then we look at NaCl. Okay, so we have an idea earlier where we had Na plus and Cl with all those electrons around it because Na gave it to the Cl. And this whole thing goes in brackets and you put a minus sign. So that's the Lewis structure of NaCl. The electrons belong completely to chlorine, so we put the brackets around there to help express that. And so to figure out what kind of bond this is, we got to go back to the electronegativity table and we say, okay, here's sodium, it's 0.9, and here's Cl, it's 2.7. So 2.7 minus 0.9. Yep, that was right, okay. Gets us an electronegativity value of 1.8. Well, 1.8 was close to 2, somewhere in this area, but it's not quite big enough to be 2. So that's pretty interesting because before we said if you have any covalent, or sorry, if you have any non-metal like chlorine and a metal like sodium together, then it's usually an ionic bond. But that usually is a really, really important thing because sometimes when you find the electronegativity difference, it's not high enough to actually make this a covalent or an ionic compound. We said it has to be greater than 2 to be completely ionic. So that means that our example here, NaCl, is actually a covalent compound. And so I probably want to draw the diagram a little bit differently. Okay, now the thing about it is it's not a clean cutoff. It's not like at 2 there's suddenly some sort of switch that happens where now it's ionic and it wasn't before. This is a gradient, so you go from being more covalent at 0 to being less covalent the closer you get to 2. Most people agree that around 2 it sort of becomes more like an ionic compound, but that's still shades of gray, right? You're increasing the ionic character as you go from 2 to 4. So basically, if you're at 4, it's very ionic. If you're at 0, it's very covalent, but anywhere in between is kind of a gray area. All right, but we can kind of use this pattern to help us figure out what kind of compound things are in general. So if you go C and H, I got to go back to the table and look at C. Let's see, where's carbon? Carbon is right here, 2.4, and H is 2.1. Okay, so 2.4 and 2.1. So we're going to go 2.4 minus 2.1. Oh, okay. So that's 0.3, so it's definitely covalent, and it's a little bit polar. There's going to be lots of things that are way more polar than that, but it's a little polar. Carbon and oxygen, we just did a second ago. So carbon and oxygen has a difference of 1, and so that puts it squarely into the polar covalent area, pretty much right in the middle. About, right about here or so. NaCl we just did, and we found that it has a difference of 1.8. So that actually puts it into the polar covalent camp as well. And then strontium Sr and F, let's see here. So strontium is 0.9 and F is 4.0. F is actually the biggest on the table, so the highest value. So our difference here is 3.1, which means that this one is ionic. Okay, so here's some more for you to practice. I'm going to put these questions into Top Hat for you to answer. Okay, so this is a summary again. I want to use the electronegativity difference of different atoms to help predict whether they're going to fall into one of these 3 categories. And so to get aluminum and chlorine, we got to go back here to aluminum, which is 1.4, and chlorine, which is 2.7. So 2.7 minus 1.4. So that gives us a difference of 1.3, which puts us squarely in the polar covalent area. So just because we have a metal and a nonmetal doesn't actually mean they're always ionic.